this is a scientific challenge that we have chosen when we started the chair, which is still there, still open, I would say, with a number of aspects, even though we have advanced here and there. The scientific challenge here for the cognitive and interactive robot, I insist on the link between both, is to devise and build the cognitive and interactive abilities for a robot that will allow pertinent, eligible, and acceptable behaviors of a robot when it is performing an assistive or collaborative action with a human. And so, of course, mentioning here the, I would say, targeted applications, insisting on the fact that even if it says here and there, this robot that doesn't exist today. They are far from existing, a number of questions are still open. So our ambition is, and was in this share, essentially to cover the full spectrum of robot decisional abilities. We are concentrating on the decisional abilities, essentially. I will give a number of examples through, I would say, 4 streams. One is a principled and long-term, I would say, multidisciplinary collaborative research about what is it to really perform collaborative action with a human and collaborative decision with human. And with this, we are working with philosophers, psychologists, ergonomists, etc. The other point, which is, I would say, our main work, is incremental development of key components for this robot, building components, one by one, and as ingredients to be integrated in an architecture that allows the robot to perform and combine its abilities to perform a task. And also, we do our best to effectively deploy AI-enabled robots, essentially prototypes, with users, and also contributing to the evaluation of this, essentially with naive users. And we have worked on all these topics, I would say, more or less. In terms of topics, I'm citing here, and I will go through these topics one after the other, quickly, to give you simply an idea of the, I would say, the scope, and also the different topics that are covered. Decision here is essentially for us, I would say, situation assessment, interpretation of situation, and planning. Planning can be long-term planning, can be reactive planning. Both are covered. And the key issue is to develop the systems, particularly in situations where a human is involved, but not only. And so, in terms of planning, we have motion planning contributions, we have task planning contributions, and we have also a topic which is in between, which is called combined task and motion planning. I will come to this. It's essentially when it is not that easy to separate hierarchically the task level from the motion level, because the problem is really intrinsically complex. And then I will give some examples of task planning also, and I will end up with architecture and also the very important topics of verification and validation or certification of robot architectures, of robot systems. So now I'll go from one after the other. The first topic is socially aware motion planning. So we have developed over years, and we are still working on this, developing robots that are able to plan their motion in the proximity or in synergy with humans. Oh, now it's working. the video was working before. Here you see a robot that is, I would say, really negotiating a passage with a human in a proactive way and facilitating as much as possible the decision and the action of the human. So this is done by making the robot plan not only for itself, but also for the human, and taking into account a number of key criteria when robot is interacting with human, which are proximity, visibility, and comfort of the human, avoiding to disturb, limiting limiting the inconvenience of the human when interacting with him. And so this system is developed and running, and we are starting to, I would say, distribute it to other colleagues and places. this notion of human-aware planning has also been extended to a robot that we have, what we call the flying coworker, which is a drone essentially with a manipulator, which performs pick-and-place operations and handing over objects to a human. And as you see here, the robot is adapting its path and its speed to the presence of humans. Here again, not only finding a path, but also avoiding to disturb or to make the human uncomfortable. Using here also the same criteria, but now it's in 3D, and it's it's a flying system. And as you see in the figures, the robot has a threshold of discomfort that it cannot go above. And this limits its speed and also the distance. So it is playing between the distance and the speed to maintain this. But still there is a task to perform. For example, a handover. This is a handover task where the robot is coming and handing over an object to the human. And here again, it's a kinodynamic planner, and the robot is able to hand over a system, an object to a human, even if the human is not in the position to reach it. So the robot computes the possible motion of a human to turn to reach the object that will be handed over by the robot. And this also here combines issues. So it's essentially here using an optimization scheme where the robot plans a path and takes into account the different criteria. Here, the complementary criteria that is taken into account is the comfort of handing over. For example, I can pick an object here, but it's not that comfortable for me. I prefer to have it here. So if this is possible, the robot will come. If not, it will give it to me here, etc., etc. So this topic is so important, and we were quite pioneer in it, that during these 4 years, we have really contributed to create a community, international community, about this topic. And it has been quite successful. For example, we have organized a number of seminars, essentially on Zoom, I would say, with a number of key partners that, as you see today, Google, NVIDIA, and even Apple are very interested in human-aware, Amazon also, in human-aware motion planning, or socially aware motion planning, as you say. And we have produced recently a paper on issues that will allow us to define principles and benchmarking of these systems. Also, there are a number of other issues I will not summarize, but essentially, we have also, I would say, collaborating directly with a number of places today, a number of universities who are really interested to have these systems running with this ability. I'm mentioning some of them here. I will not go into detail. Of course, the slides will be available. Now, concerning combined task and motion planning, where am I? Okay. As I mentioned, this problem here also, we have been pioneers in formalizing this problem years ago, almost, I would say 15 years ago, and obtain some result. The issue here is that in some situations, you cannot simply, as it is very often done, separate a problem into task planning, defining the set of pick-and-place operations to perform an action, and then the motion. For example, for this first example of a robot, if you ask the robot simply to move the red object from this place from the shelf to the floor, it is a simple pick-and-place operation. So if there is no obstacle, it will be done directly. But here in the situations, it will be necessary for the robot to move all the other objects that are blocking it to perform these tasks. So a pick-and-place operation is transformed into a sequence of pick-and-place operations, which are not the goal, but allow I would say the task to be performed. So the problem with this is that it is combinatory explosion. It's explosive. It's a huge problem because essentially you explore the configuration space of all the objects of the robot and finds where to link them. And it has been shown that it is very complex. What we have done recently with one student, Ismail, is using deep learning in order to speed up very strongly the planning process by accelerating a key operation there, which is the computation of the feasibility of a place operation. So we have developed a network here which essentially predicts if an action is feasible, and also the probability of each type of grasp, I would say the feasibility of each of the grasp. And this is used to give, if it is positive, to give a rich information to the task planner. And having this, we have been able for this kind of problem that I was mentioning, first to solve the problem, but also to show that we speed up with very significantly, 94%, the speed of a standard planner using these deep learning techniques and this kind of network. So you would say you were showing a robot manipulating boxes. It has been extended recently to manipulate other types of objects, as you see, real objects, and also to do multi-robot task pick-and-place operations like you see here. And all these problems are, again, very intricate. It's not possible to separate the task from the motion. You have to take both in the same time because you change one small parameter, you change the size of an object, you change the size of a robot, and the plan changes completely, drastically. Task planning now, the full task planning. We had a number of contributions here. I'm mentioning some of them here, essentially, going from really advancing I would say, the core algorithm of planning, taking into account, for example, temporal constraints, to other topics linked to learning or to acting and deciding in interaction with the robot. So I will go through this very quickly again here. The first one, this work essentially from Arthur Bitmono. We are developing, I would say, in-house solver that has been used for a temporal and hierarchical planner. And it also has been distributed in the framework of an international project. Another topic is the temporal plan execution based on taking into account partial observability. I will not have time to go into details, unfortunately, but all of these topics are by themselves very interesting. Another issue that has been taken into account this is the work of Philippe Rai, is developing a system that is able to learn hierarchical planning models based on action sequences and demonstrations from human, and extract the hierarchy of the decomposition of the task to be used by the planner. Other topic that has been used is an architecture for high-level control of a fleet of robots, taking into account here again time and resources. Other topics that we are looking at now, I'm moving to decisional issues concerning more the humans. We have also here a number of contributions. This contribution is essentially here. Unfortunately, it seems that it's running. What you see here is a situation assessment system that does not assess the situation only based on perception, the object that it is tracking, but also using a physical simulator to continue to estimate what is happening. So, for example, the robot here is able to, I would say, to follow the fact that the object has been moved forward from one box to another, even without seeing it, simply by using the simulator to continue to track the object where it goes when it is moving. Another topic that is very important in this situation assessment between human and robot is to develop in the robot the abilities to take into account the perspective of its humans, to build an estimation of the mental state of the human, which could be different from the robot because of the special positions, and also because of past experience. The human have seen some events, and the robot have seen other events. And based on this, the robot here is performing a reference action, very simple. It's a verbal action, but doing it in a grounded manner. First, referring an object based on what is seen, or its shape and what is seen, and also what the human sees, and not only what the robot sees. And we have developed an algorithm that the robot is able to do this in a minimum and non-ambiguous situation. Also taking into account past experience, as I mentioned, with managing the beliefs of several persons present in the scene that do not share the same experience. Another topic that I will not detail very much is human-aware task planning. I will not detail this very much because essentially you will have a lightning talk by Anthony Favier on this topic specifically. He worked on it, where here essentially again the robot explicitly take into account the human as independent of itself and reasoning on the I would say the beliefs and the abilities of the human, and using this to produce plans that are feasible, pertinent, and acceptable by the human. Also adapting to this. Anthony will give far more detail about this issue. So I will switch this for saving time. The last topic is robot control architectures. So as I mentioned, we are developing architectures that combine these different abilities, motion planner, task planner, situation assessment system, dialogue system, and combining them into an architecture based on, I would say, 3 minutes, very good. And combining them. So we are building architectures, and comes the issue of building components and certifying the components and also certifying the architecture. So we have a topic of research that is conducted by Félix Ingrand, essentially, who based on the specific language that has been developed years ago, which is on genome, a number of tools have been developed to in offline manner and online manner to validate and to verify and validate the I would say the sequencing of the component. And also more recently, there is an extension now for the higher level, which is the task level, the programming of the task, which also will produce, I would say, will be compiled in a way to be then used by a model checker, TINA in this case. To conclude, I will switch this because I don't have time. Concerning the robot verifying things, we have also developed the ability for the robot online to verify that it is effectively performing good somehow. And so we have some interesting contribution again here with psychologists to make a robot that is able to verify online the quality of the interaction. So basically, this is, I would say, the core research. Concerning project, we have been involved in a number of them. I will not give any detail here. The only thing that is important is that this work has allowed us also to set up new objects that will start now and for several years on these topics and on different, I would say, aspects of the topic. And I will simply finish here with an example of deployment of a robot running these key components. Okay. This is a robot performing guiding, but using perspective. Thank you.
Other questions? While Nicolas is setting up all his material. So Rachid, you said that all what you presented are currently implemented in one robot or in one system. No. What is the status regarding that?
No, of course, it depends on which topics.
Because I guess that the idea is to have everything integrated in one system, right?
Yeah, of course, but it depends on the application, because then you run specific, for example, for a robot with a manipulator, it will be different from a outside rough terrain robot, or if you have a system where the robot has to collaborate with human or simply to act in presence of humans. So this creates different issues, but essentially the basic function and the algorithm can be reused in different systems. And the architecture is generic.
But are we far from having everything covered?
We have been able to integrate from time to time for a given experiment, like the one I've shown here, all the components for a full task. Okay, and we are able to do it again and again.
Okay. Thank you very much, Rachid. I don't know if there are any more questions in the audience. No. Okay. Thank you very much, Rachid.